Alright, so at this point, you're probably sick of, when trying to find f prime of x, working out all of the algebra associated with something like this. Either huge polynomial expansions, or there's square roots, and trying to work out what all of that means and that sort of thing. It's a lot of work to try to simplify this thing algebraically, and you must have by now noticed some patterns or shortcuts that will allow you to make this a little bit easier. So we're gonna do that here. So f prime of x is this thing, but we want to find maybe some general rules of how derivatives behave. So first of all, if I take the derivative of a of f of x plus b of g of x, where a and b are constants, it turns out that this thing behaves pretty much exactly the way you hope it would behave. That is, what you get is a times f prime of x plus b times g prime of x. And the reason for that is based on the limit definition of a derivative. So let's kind of work this out here. This thing is equal to the limit as h approaches 0 of a of f of x plus h plus b of g of x plus h minus a f of x minus b g of x all over h. And what we just noticed is that we have a big old fraction over h. We can rearrange all of these terms, and we can separate the fraction too. So we get the limit as h approaches 0 of a f of x plus h minus a f of x over h plus b g of x plus h minus b g of x over h. But you might remember from 2 chapters ago that whenever I have the sum of limits, I can rewrite that as or a limit of a sum that's the same thing as a sum of limits. And I can factor a common a out of this first thing, and I can factor a common b out of the second thing. And this whole thing here is just a f prime of x, and this whole thing here is just b g prime of x. And so that is the proof that this facts hold. And this is very nice. What allows us to basically say is, look, if I have a sum of a bunch of stuff, I'm really just trying to find the derivatives of the individual parts. And I'm not only just trying to find the derivatives of the individual parts. If there's constant multiples, I can just ignore them and focus on the derivatives of the non-constant portions. And so that fact is going to make our lives much easier. All right, another fact is that the derivative of x to the n is nx to the n minus 1. And the reason for that is well, when we're evaluating, say, terms like x plus h squared minus x squared, you'll notice that this is x squared plus 2xh plus h squared minus x squared over h. These two cancel, and then this cancels with this, and this comes down to a 1. And then if I plug h into 0 into that, I'm just left with the 2x. If I have x plus h cubed minus x cubed over h. Then I get x cubed plus 3xh, x squared h plus 3xh squared plus h cubed minus x cubed over h. This cancels that, and that becomes a 1, becomes a 2. And now if I plug in 0 for h, those two go away, and I'm just left with the 3x squared. So the limit of x plus h to the n minus x to the n over h will give me x to the n plus n x to the n minus 1 h plus a bunch of other stuff with higher h powers, eventually culminating with h to the n minus x to the n over h. This and that cancels. This cancels that, cancels that. When I plug in 0, I just get nx to the n minus 1, which is this fact here. And so once we've established these rules, we don't need to reinvent the wheel in order to establish what certain derivatives are. So for example, if I want to know if f of x is x cubed plus 3x squared plus 6, this is the same thing as x cubed plus 3x squared plus 6x to the 0. And so f prime of x will just be 3x squared plus 6x to the 1 plus 0, because the 0 comes down and kills the 6. Plus 6 is a constant function, and so its derivative is always 0, and that's what I get. If my g of x is 3x plus 6 square root of x minus 2 over x, that is the same thing as 3x to the first plus 6x to the 1/2 minus 2x to the negative first. So its derivative will be 3x to the 0. The 1 comes down, and that power goes down, plus 3x to the negative 1/2. That power comes down, it decreases by 1, right? Power comes down, decrease by 1, plus 2x to the minus 2. And certainly you could simplify this algebraically further, but that essentially gives you that solution there.